Good afternoon. I'm Corey, and I'm here with Tomasz. And today we're going to be talking to you about MLflow, a platform for the complete machine learning lifecycle. MLflow is an open source project that initially got its start at Databricks, and it's developing a large community following. To start off, let me provide an outline of the topics that Tomasz and I are going to cover over the course of the next hour. First, I'll talk about the challenges associated with machine learning model development. Then, I'll address how MLflow tackles each of these challenges. Tomasz and I will also provide an overview of the three main components of MLflow: tracking, projects, and models. And then finally, Tomasz will tell you all how you can get started with MLflow and contribute to the project. So let's dive right into those challenges. As a lot of you are probably painfully aware, developing machine learning applications is difficult and complex. And to expand on that a bit, let's take a look at the typical machine learning lifecycle. It all starts with the collection of raw data. Once data is available, it is then cleaned and featureized. And this cleaned data is used to train a model. Finally, this model is deployed to a variety of production contexts, whether that be a web application or a batch streaming environment, for example. Oftentimes, these production applications receive new data, which can then be fed back into the first stage of the next iteration of the lifecycle, and it repeats. So at the surface, this may sound pretty simple. You got a four-stage process for developing machine learning models and applications. But there are several layers of additional complexity that make this a very difficult lifecycle to implement effectively, especially for large organizations that need to operate at scale. So let's take a look at that first challenge that we may encounter. If we were to sit down and attempt to implement a solution for each stage of the lifecycle, the first thing we find is that we have a large number of available frameworks that can be implemented in order to do raw data collection, preparation, training, or deployment. But there really isn't a unified framework that allows us to do all of these things at each stage. And what that means for an application developer is you're often trying to figure out how to stitch together your Kafka data store with a Spark ETL pipeline. And it becomes a very difficult task, especially when you consider the fact that machine learning practitioners in the training phase are often encouraged and incentivized to experiment with a bunch of different machine learning frameworks. This means that data scientists may be attempting to train models in TensorFlow for deep learning, alongside more traditional models like regression techniques in scikit-learn. And these two frameworks are just a couple of hundreds of popular machine learning libraries that data scientists depend on every day in order to produce quality output. Finally, at deployment time, models trained in this variety of formats need to be deployable to this variety of production contexts. That means that it should be just as easy for me to deploy a TensorFlow graph for real-time serving using a product like Amazon SageMaker as it is to deploy a scikit-learn model for a batch streaming context, for example, inside of a Spark job. So assuming that as an organization you can stitch together all of these different frameworks and make this happen, your work is not done. We also observe that hyperparameter tuning is an extremely important concept in machine learning. See, models are configurable, and they're highly sensitive to certain numeric parameters that dramatically affect their performance. For example, selecting the incorrect set of parameters can produce an output that's no better than guesswork. But selecting the optimal set of hyperparameters can produce a model that revolutionizes a business use case. And so it's absolutely imperative that when developing a machine learning platform, data scientists are capable of adequately exploring this parameter space and tuning their models so that they work exactly the way they want them to. And finally, assuming this all happens at scale, the last major hurdle is model exchange and governance. See, it's not enough to just train a machine learning model once in isolation. For every model that comes out of training or is in production, an organization should have a complete understanding of exactly how that model was trained. And that includes the source code that trained the model, the version of that code, who trained it, and a bunch of other important metadata. And this information doesn't just have to stick around for a week. Potentially for businesses that are operating in more privacy-sensitive or scrutinized conditions and using machine learning, this lineage needs to be kept for every model that's trained, potentially for years. And clearly, this is a lot more of a challenge than we initially estimated. So now that we've fleshed out these layers of the machine learning lifecycle implementation, it's pretty obvious that this isn't just a simple 4-stage process that can be implemented by one or even potentially tens or hundreds of engineers. It's a quite challenging problem. And this is reflected when we talk to certain customers before building MLflow, and we ask them about their challenges. A chief scientist at an ad tech firm said, "I build hundreds of models every day to lift revenue, and I use any library. That may include MLlib, PyTorch, R, and more. But there's no easy way to see what data went into a model from a week ago, tune it, and rebuild it." And we're just talking about a week, not even a longer time horizon. Additionally, another consumer electronics firm says that their company has 100 teams using machine learning worldwide, and yet they can't share their work across those teams. When a new team tries to run some code, it often doesn't even produce the same result. And so this is that reproducibility problem of model exchange and governance that organizations are encountering on a regular basis. Which leads me to the motivation for MLflow. We derive a lot of inspiration from 3 organizations that have actually had a lot of success in this arena. Facebook with their FB Learner platform, Uber with Michelangelo, and Google with TFX. If you're using one of these systems, you get the standardized machine learning lifecycle from ingest to preparation, training, and deployment. And this all happens right out of the box. The problem is that unless you're fortunate enough to work within one of these organizations, these platforms are tied to a specific company's infrastructure, and they're not open source. Additionally, they often provide first-class support for certain machine learning frameworks. For example, TFX is awesome for TensorFlow. But if you're an R developer, you're probably not going to be able to leverage all of the benefits of that platform. And so this leads us to the motivating question. Can we provide a complete solution for the machine learning lifecycle in the same fashion as these 3 major organizations, but in an open source fashion? And can we support the wide variety of machine learning frameworks that data scientists depend on every day? Introducing MLflow. We're an open source machine learning platform. We work with any machine learning library and language, and it's designed to be run the same way anywhere. Meaning if I train a model on an external third-party cloud service and I want to rerun it on my local machine, that should work in a reproducible fashion the same way every time. Additionally, MLflow is designed to be useful for a single data scientist operating in isolation, just as much as it's designed to be used by thousands of data scientists and machine learning practitioners across a large organization. And with that, let's take a look at the 3 major components of MLflow. I'll start off by talking about MLflow Tracking. This is a centralized repository that collects all of the critical information about machine learning training sessions that occur within a data science group. Then, Tomasz will talk about MLflow Projects. This is a reproducible format for machine learning tasks, ensuring that they can be executed on any platform and reproduced at any time. And finally, Tomasz will talk about MLflow Models, a generic model format that allows any model produced with MLflow to be deployed across a variety of production environments for real-time scoring, streaming, and batch processing. Let's dive right into the key concepts in tracking. As I stated before, the primary goal of MLflow Tracking is to provide all of the critical information about each machine learning training session that occurs. And this means that we're interested in the following attributes. The tracking server keeps track of those important parameters that so dramatically affect model performance. And it also stores the metrics that provide a window into the effectiveness and accuracy of a machine learning model. Additionally, and arguably most important for reproducibility, the MLflow tracking component can store the models themselves. This means that if I train a deep neural network in TensorFlow, I can take that graph and persist it on the cloud so that it can be read back by a variety of other users who may be interested in rerunning that model. Additionally, for lineage, the tracking service allows for the storage of source code, as well as the version of that code. And that can be as specific as the git commit associated with a project that produced a machine learning model. And then for anything that isn't explicitly supported as a first-class entity in the centralized tracking ecosystem in MLflow, we provide an API for specifying arbitrary tags and notes associated with a ML training session. Meaning, for example, a data scientist working on a content recommendation model can specify some information about the business use case, for example, that model was produced for. Now that we understand the concepts, let's see how MLflow Tracking integrates within the existing training ecosystem. When we looked at the workflows that many data scientists use in training machine learning models, we found that they prefer to perform their data science tasks in different places. Some may prefer to use distributed hosted notebook environments like Databricks. Others are much more comfortable doing machine learning on their local machines. And a third group prefers executing machine learning jobs remotely using large scalable cloud services. In all of these cases, MLflow provides a tracking API that's available both in Python as well as in a RESTful format that can log all of this critical information about source code and artifacts and parameters to a centralized location. And therefore, it doesn't matter where the model is being trained. All of this information is collected accurately every time. Once the data has been aggregated, the MLflow Tracking server also provides an API as well as a user interface for exploring information about all of these trained machine learning models and training sessions. This is a sophisticated user interface that allows users to compare the accuracy of a model to various parameters that it was configured with, as well as sort based on evaluation metrics to find the optimal model for their use case more quickly. Let's take a look at the API that users can integrate into their existing machine learning training code to log all of this important information. It's very simple and it's very thin. The first step is to create a new machine learning training session using the MLflow start run directive. For reference, we call machine learning training sessions runs in MLflow. The next step is to log those very sensitive and critical parameters about the model using the MLflow log param directive. After that, it's very simple. The user just pastes in their existing training code. This could be a routine to train a TensorFlow model. It could be code written for scikit-learn estimation or in a variety of other frameworks. As long as it produces some model, it's compatible. After that, the user evaluates their model against some validation or some test data. And this produces metrics that provide insight into how well the model performs. They can log these metrics to the tracking component using the MLflow log metric directive. And if there's any more sophisticated data, for example, if we want to know exactly which data was used to train that model, that can be logged as an artifact using the MLflow log artifact directive. And then finally, the model itself is persisted using a variety of convenience routines for saving models in different frameworks as the MLflow compatible format. In this case, we show an example call that saves a TensorFlow graph in MLflow model format. So now that we've seen exactly how this API can be integrated into existing training code, we're going to walk through a demo and do it live. The goal of this demo is to leverage an existing public data set of Airbnb listings data and attempt to train a regression model that predicts the price of a given Airbnb listing based on other attributes. So the first step is to check out our existing training code that doesn't have any of the MLflow hooks embedded. Everybody see that okay? Awesome. So let's walk through the structure of our existing training code. At first, we define a couple of hyperparameters, those sensitive values that are going to affect model performance. Then, we load model data, both for training time as well as testing to produce validation metrics. Next, we leverage the scikit-learn model framework to train a model using ElasticNet regression in order to fit our data and estimate prices based on Airbnb listing attributes. Then, we perform a simple evaluation routine, passing in our test data and retrieving some metrics about the performance of the model. And we also print a standard out just to make sure that something happened. What we're going to do now is embed the calls that would be necessary to track every single run of this script using MLflow. The first thing we're going to do is create a new MLflow run using the MLflow start run directive. And we'll move the remainder of our code into the context generated by the start run directive. Then, after our hyperparameters have been specified, we'll log them using the log parameter method. After that, the model is trained and our metrics are evaluated. We can log those as well. Additionally, in this example, we created a more sophisticated performance plot that allows us to determine how this model is performing in pricing listings. We'll log that as an artifact as well. And finally, and most importantly, we'll log the model itself. And that's it. All we had to do was paste in several small changes to our existing training code, and we have complete compatibility with the MLflow Tracking ecosystem. So let's go ahead and run this script and see how it works. And while this is running, we'll go ahead and start the MLflow UI. This will allow us to visualize information about the training session that's currently running. Awesome. So what we see is that we just trained our scikit-learn estimator, and we got some metrics such as mean absolute error and an R2 value. So now let's hop over to our UI. Now that might be a little tough. I'm just going to start this up again real quick. I'll give it another couple seconds. That's promising. Anyway, maybe we can move on to the next section of the demo and we'll see all the runs as they were initially produced. Oh, actually, this looks like this finally came through for us. Awesome. Can everybody see this clearly? Cool. So we trained our model, and we have a new MLflow run. You'll see that those same metrics that were produced are available and visible to the user. Additionally, the parameters that we trained with, in this case, we just defaulted to alpha values and an L1 ratio. These are the parameters for our model of 0. And then we have information about the user that trained the model. In this case, this came off my local machine. And we have the actual version of a Git repository that this code exists in. So this information helps us preserve the lineage of the training session. If we take a closer look, we also have those artifacts, that detailed performance plot, which can then be visualized. And this has already been saved as an artifact and is available. We also have the training data that we explicitly logged. And we have the model itself in MLflow format. There's an ML model file that contains all of the necessary information for reproducing this model on a different machine. We include the version of Python it was trained in. We include the version of scikit-learn, as well as the serialized scikit-learn model artifacts. And all of this information is expressed as a Conda environment so that users who are familiar with the Conda workflow can activate it and immediately clone and reload the model. The next step is to perform a little bit of hyperparameter search and see how the MLflow UI can help us select the model with the optimal parameters for a given use case. Let's take a look at a simple script that was written in order to perform sort of a basic hyperparameter iteration over our two parameters. We have the alpha and the L1 values ranging over a small subset of potential options. And for each of these values, we're going to run our training script, and then we're going to see how we can compare the runs against each other to achieve a more optimal decision about which model does the best job of predicting listing prices. So let's go ahead and run this. And essentially, all we're doing is just rerunning the same script for various parameter values. So you'll see that for each selection of parameters, we're getting different metrics results, and all of these are being persisted in real time to the UI. And what we're going to do after this is actually visualize how the parameters affect the metrics output. And hopefully that visualization will be somewhat illuminating. So while this is running, if I were to refresh the UI, I should see that we're getting a lot more information about the different machine learning training sessions that have been initialized. So here we have a lot more information. And if we take an eagle's eye, sort of bird's eye view at this, we can see that there's this correlation between the R² value and the mean absolute error. What we find is that for smaller values of R², it seems like we get more error. So maybe we should use the MLflow search functionality in the UI to filter our results and ignore some of those with the lower R² values. And we can do that by typing in a very simple SQL-esque search query. We will restrict the R² value to being greater than 0.26. And if we do that, and we take a look at the filtered runs, we see that all of them match that predicate. Then we can select our remaining information and perform a comparison between the different training sessions. We can plot, for example, how the L1 parameter relates to mean absolute error. In this case, this isn't a super illuminating context. It looks like regardless of parameter value, you're sort of seeing the same error. But you can imagine that for models that are highly sensitive to certain parameters for performance, this kind of visualization technique is extremely useful in determining at a quick glance which set of parameters is optimal. And that concludes my portion of the MLflow Tracking demo, but there's a couple other concepts that I would like to talk about addressing how the MLflow Tracking component could be integrated within your existing infrastructure. So MLflow divides its tracking components into a couple of different concepts that are abstracted. The first is an entity store. This is a file store that persists all of the metrics, parameters, tags, and notes associated with a machine learning training session. Basically anything that's lightweight and isn't a large blob, for example, an artifact. And users can leverage existing implementations of a file store that's available on their local host, as well as a RESTful-based server that can be integrated into existing infrastructure. We're also working on a database backend, possibly looking at using SQLite or some other more heavyweight database implementation to fully optimize this entity store. The other component is an artifact repository, which allows users to store their existing machine learning models as blob data that can then be reloaded. So this would store all of the TensorFlow graphs, scikit-learn estimators, R functions, for example, that are saved as MLflow training sessions. And this is available in a variety of different formats. And we define a relatively abstract and easy to implement API for integrating additional blob stores into MLflow for the purpose of acting as artifact repositories. We provide support out of the box for an S3-backed store. We also provide support for platforms like Google Cloud Storage, as well as the DBFS artifact repository on Databricks. So chances are, if there's a major blob store that you want to use to persist model artifacts, MLflow is compatible with it. Now, I'm going to hand it over to Tomas, who's going to run through the deep dive of the MLflow projects and MLflow Models components.
Right. Thank you, Corey. Okay. So again, I'm going to continue where Corey left off, and I'm going to talk a little bit more about the other two components of MLflow, which is MLflow projects and MLflow models. MLflow projects is a packaging format for reproducible runs on any platform, and MLflow models is a general format that supports diverse deployment tools. But what you can think of both of these as kind of like a wrapper around training, which allows you to run the same training code in any environment, and then the wrapper around scoring, which allows you to deploy your models into any environment. Right. So here's the outline for the two parts of the talk. I'm going to talk a little bit about motivation for both, and then give a quick overview, follow up with an example, and a short demo, and then in the end, I'll wrap it up. Okay, so what's the motivation for MLflow projects? Why do we think that this is important? So in a modern machine learning environment, you have like many different tools. So you have PyTorch and XGBoost and TensorFlow and scikit-learn and R and Spark, and the list goes on. And unlike in many other disciplines, you often actually need to use several of those tools in the same project because different tools produce different results and different problems, and sometimes you might need to try a couple of them to get the best result for your problem. On top of that, there's often situations where you have diverse set of data scientists on your team. They might be familiar with different tools. So it comes up quite often that people combine multiple tools on the project. And then to make things worse, you have diverse set of environments where you might want to run your code. Right? So you have your local machine like Mac or Linux or whatever, and then you have all these production environments based on Docker or Databricks or Kubernetes. And the result is that it is quite difficult to productionize machine learning code because it often happens that your code has dependencies you didn't cover. Different version of the library leads to different results, and people struggle basically reproducing their results in different environments. So the vision of MLflow to tackle this problem is to have this MLflow project which encapsulates basically everything that is needed to run the project. So it encapsulates the code, it encapsulates the configuration, and it encapsulates the data. And then on top of that, we provide APIs which allow for either local execution, again in different environments, or for remote execution in production, or maybe on a beefier machine on EC2. Right, so here's a little bit more detail about what MLflow projects are about. So it is a packaging format for reproducible ML runs. The kind of key design principle of MLflow is that it should be easy to get started. So we try to make like as few obstacles for you to incorporate this into your existing tools as possible. So actually any code directory or GitHub repository will work as an MLflow project. But you'll get most benefit if you include this ML project file, which tells MLflow kind of what's inside, what are the dependencies, what command to run. And it allows you to abstract from how that particular project is implemented. Now, the dependencies can be defined by either conda environment or R dependencies file, in the future also Docker. And the idea is that with the dependencies being part of the project, you get reproducibility in any environment. And then, as I mentioned before, on top of all this, we have these APIs which allow you to run it in different environments in different way. So we have a CLI where you can execute projects from the command line. We have clients for Python, R, and Java, which allow you to execute the projects directly from the source code. Now here is an example how MLflow project looks like. So you can see that it's basically a directory structure with code and then some extra stuff. And the extra stuff is, let's start with the ML project file. So it is a file which contains configuration of your machine learning project. In this case, you can see that it specifies conda environment, which has the dependencies. And then it has a list of entry points. In this case, there's only one entry point called main. But every entry point is essentially a command you can execute. It can be to train your code or different versions of training your code. And the entry point has a list of parameters. And then it specifies a command to run. So this actually is pretty powerful because different people use different formats on the command line. Different languages are invoked differently. So this kind of allows you to abstract of whatever is inside. You have just like one unified interface how you can execute whatever the ML project is. And now here's an example how you can run it. So let's say if this project was sitting on Git, I can execute it directly from Git, in which case MLflow will log the Git hash, and you get exact version of the code that ran. And I can run the same from Python. Okay, so now I'm going to show a quick demo of how ML projects work in practice. So let's, I'm going to continue in Corey's example of the, predicting prices of Airbnb listings. But in my case, I'm going to have like these two data scientists who produced, who provided code in two different languages, and we will see how we can inspect and run their code and change parameters and improve on their results. Okay, so here's my MLflow tracking server. I actually already ran one run myself, but I would like to focus on the later two items. So we have Erin, who ran this project called Spark Summit by XGBoost project. And if I click on it, it takes me to the GitHub repository. And it's because he ran the project directly from Git. And I can see that there's a bunch of files, and there's some Python source code. But it's kind of difficult to see what exactly is going on. And then, because he ran it with MLflow, we have the list of parameters he used, and we have the results here recorded as RMSE and validation set RMSE. And then we have Amy, who provided the code in R, actually. And similar thing, we can go to the GitHub and see her source code. And she also provided RMSE and validation RMSE. Her code seems to be doing a little bit better, but first of all, let's see if we can reproduce the results, right? Like if we can run it ourselves. And so one option I have to run the code is from the command line. So let's execute Amy's code first. Let's say in this case, I might not know anything about R. I might not know what sort of libraries she used within the R. I can just simply execute MLflow run and the GitHub repository. We're training. And we should see the results in shortly. Right. So we have a new item, and we can see that we get same results as before. And now for running the Python, I can run the project in the same way. But maybe let's try something more interesting. Let's see that Amy, who is an R user, doesn't know maybe much about Python, but she knows something about XGBoost and gradient boosted trees, and maybe she noticed that the parameters Erin used don't look quite right. So she can actually execute Erin's project directly from R without again knowing anything about it. So she can just call MLflow run and give it a URI pointing to the same GitHub repository, and then she can get parameter list where she says like her own hyperparameters. Right? And we can execute the code from RStudio as she's used to, and it failed. Seems like I'm missing. Seems like for some reason I lost my conda environment, but. In principle, this is how she could run if she didn't mess up her conda environment before. There should be a simple fix, but I'm going to have to continue with my presentation. I might get back to it later. Okay, so now let's follow up to the MLflow models. First, the motivation. Why do we think that MLflow models is important part of machine learning workflow, or tool for managing machine learning workflow? So it's really similar motivation to the project. We start with the same diverse set of tools as we had for training. These all tools can produce some form of a machine learning model, which sooner or later we would like to put into production, right? And then for production, it's actually even worse in this case because we have many different modes of production even, right? So we have real-time scoring as a REST API endpoint, which can be deployed somewhere in Docker or maybe on SageMaker. And then we can also be interested in scoring big data in batch, let's say on Spark, right? And so the list of potential deployment endpoints is even bigger here. And with the list of tools, what we get is like this, unmanageable end-to-end mapping, where you would basically, every tool would have to provide ways to score on every potential endpoint, and that's clearly not manageable. So the vision of MLflow in this case is to have this unified MLflow model format where all the tools can represent their models as the MLflow model, and then all the endpoints can then provide tools to deploy MLflow models into them, right? And the idea is that this is like kind of an abstraction barrier, and neither sides have to know details of the other one. Right, so let's take a closer look on what MLflow models look like. So it is a packaging format for MLflow models. The format is similar to the projects. It's a directory structure with some model-specific data and some code, and it contains this ML model file, which includes configuration for the model. Similar to projects, we define dependencies by using the same tools, so Conda and R dependencies, and in the future Docker. And similar to projects, we include APIs to deploy the models, right? And we have, again, APIs for CLI, Python, R, and Java. Now here's an example of how ML model looks like. So in this particular case, we have a directory structure with some model-specific data. In this case, it's a TensorFlow model. And then we have this ML model file with configuration, right? And you can see that the configuration includes the run ID, so we can always trace the model back to the run which generated it. We know when it was created. That's important. And then there's this list of flavors, which I'm going to talk a little bit later in more detail. But flavors is basically different representations of the model for different purposes. In this case, we have TensorFlow, and then we have Python function. And TensorFlow is useful for all the tools that know how to deal with TensorFlow models. And Python function is useful basically to anybody who wants to deploy the model without knowing what the model really is, right? Just knowing that it's a Python executable. And now here's how you would log such a model. So you would use MLflow TensorFlow log model, and then MLflow takes care of it. So let me talk a little bit more about the flavors of MLflow models, right? So any model can log multiple flavors, and the purpose of this is that we basically cover all the possible use cases you might have when applying the model. So for instance, the model we looked at earlier, someone might want to pull it back to TensorFlow, extend the graph, tweak it, and score it. Someone else might just want to score it without knowing anything about it. In some cases, for example, for Spark models, they can be exported as in the MLib format, which provides more efficient online scoring, right? Or Spark format, which provides better support for batch scoring in Spark. So the flavors is like really a tool to give us flexibility to represent any models in several different ways. Now, let me talk about the PyFunc, which is the generic Python model. So the idea of a PyFunc is that it's a very generic model which can really represent any potential model representable in Python whatsoever. And it is, as such, it is defined as a directory structure with these components, some of which are optional. The only mandatory part is that it includes a link to the loader which can load this model. And the loader is Python package which must be visible during the loading time, right? But in addition, you can specify any code dependencies, where the code will be just packaged with the model itself, any potential data dependencies, and an environment with Python packages that you require to run. Because the Python model makes, or the PyFunc model makes very few assumptions about what it has to provide. Basically, any existing model can be represented as a PyFunc model, and then MLflow provides functionalities to work with this model. For instance, any Python function model can be deployed as a REST API server. It can be deployed to SageMaker. It can be deployed to Spark as a Spark UDF. Basically, by including this Python function flavor in your model, you get all these things for free. So it's a great flexibility. OK, so now we're going to go back to the demo. And I'm going to show how, in the first part, we've generated some model in different languages. Now we'll see how we can score them. So first, we can. I kind of didn't really look into the details of the run in the first part of the demo. So maybe let's take a look on what sort of models we have. So we have the model generated in R. And we can see that it has the familiar ML model file. And we have flavors here, Keras, because it's a Keras model, and then Python function. And then there is some model-specific file, in this case, H5 file with configuration. And then here we have conda environment, which includes dependencies, in this case, MLflow and Keras 2.2 or greater. So let's take a look how we can put these models into production. Right. So we have these models, and they are sitting on the tracking server, right? So I can refer to them by their run ID and their artifact path, and they all provided Python function as one of their flavors. So I can now use it to predict it without really knowing much about the models. So by using MLflow PyFunc predict, I can score basically any model sitting on which provides Python function on which data. So let's just score one of these. Yeah, and you can see the MLflow in this case quietly activates the conda environment, runs the model with all the dependencies, and then just returns me the results. Similarly, I can serve the model as a REST API endpoint. And again, all I need to provide is run ID and the artifact. I don't need to worry about what sort of model it is. And then I can query it, let's say via curl, and I get the same results. Now for maybe more interesting example how I can use this model in diverse environment. So maybe I have this big data set sitting on Spark, and I want to make sure that the model behaves as expected on big data as well. So I can actually easily pull it into Spark, turn it into a Spark UDF, and then score it on big data. So here I just read the data from Parquet format. Here is the example of the data with details of the columns. And I set the MLflow Tracking URI to the server I used, in this case called Databricks. And yeah, this is where I pull the model into Spark. Basically, again, all I need to know is the artifact name that I call simply model, the run ID, which generated the model, and I get my Spark UDF. And applying Spark UDF is simple, as I'm sure many of you know. I just go to the data frame, and I have my results. Yeah, and the model seems to be behaving same on big data. So no surprise there. Okay, so that concludes the demo part of the models. Now, we don't really have too much time left in this talk, but there's also more advanced parts of MLflow that you can check on our website and work with. We have examples that you can try for more advanced use, right? So this was like a machine learning basics, but in reality, you probably want to do more. So one example of such advanced use case is hyperparameter tuning, right? Which is critical part of machine learning workflow. It kind of reduces the variance of of your machine learning process, and it gives you automation rather than manual tuning and uncertain results, right? And then if you check our examples, there is an example how you can do hyperparameters with MLflow. Here is a basically conceptual picture, and you can see that even such a thing as hyperparameter tuning can benefit from MLflow in several fronts. So one big benefit we get from MLflow here is that we can basically have this hyperparameter tuning project, which can then execute any other MLflow project, again, like across language boundaries, different notations for command line parameters. Basically, you can take any particular project and tune it with your hyperparameter, with your favorite hyperparameter algorithm. Now, everything is logged with MLflow Tracking, so you can inspect the results and have history of those for later use. And we can log MLflow models and deploy them later to production. Other example of advanced use of MLflow is multi-step workflow. Again, this comes very common in real use cases where maybe you have like a big data which come in, they need to be preprocessed. Eventually generating training data set, which you might want to apply on different machines. Because, for instance, if you want to train TensorFlow model, you might want to train on GPU machines. But the ETL is better to be done on like standard cluster. So you can use these multi-step workflows to to combine basically different projects together, chain them, and get your results. Now, to get started with MLflow, we are on pip and on CRAN. So for Python and R, it's really easy to get started. You just type pip install MLflow, and you can start using it. You can find docs and examples on mlflow.org, also on our GitHub. And we have a Slack channel where you can ask questions, and we'll answer. Now, the ongoing roadmap. So MLflow is still a relatively new project. It's under intense development. There is plenty of new features and functionalities which are coming, also based on demand from our users. So, please check it out and be active on all the channels. And if you have stuff that you think is missing and would really benefit you, we'll be happy to add it. Okay, so to conclude, the tool like MLflow can greatly simplify the machine learning lifecycle. It can allow you to abstract from details of individual machine learning projects and make sure that you can keep track of your results, be able to reproduce your code, and deploy it to production. Thank you.